Yeah, I'm Pete Mendygral. I'm from HPE. So my talk is actually going to be not so much on like developing for DAOS, but building workflow systems around it, in particular, and applying them to training LLMs. So this is based on some open source work we have in another project that I'll kind of walk through today. But to motivate the efforts, AI HPC workflows themselves are, much grander than just an application. We're used to HPC situation where there's a simulation code. It's a single monolithic thing. It writes checkpoints and stuff as onto as itself. But workflows actually consist of multiple applications, or even just Python interpreters running functions in coordination with MPI applications. The world's getting a lot more complicated as we bring AI capabilities together with HPC to do things like AI-informed coupling and such. So workflows could just be simulation ensembles. Those have a collection of state across multiple instances of applications. Coupled AI training, inference with simulations, even more complicated. And there typically is some kind of coupling layer, some mechanism that they use to exchange information. So something like if I want to run inference on a model, train a model, and actually deliver data to that model during training, there's some kind of information exchange layer. And that could be something as simple as the file system, which is often how people do it, or it could be something much more sophisticated, and that's sort of where we're going with the project that I'll talk about in a second. But using LLM training is a specific type of workflow. So again, I think we're generally tempted to treat training like another monolithic MPI style application, but that's increasingly becoming less the case, especially with things like mixture of experts style training, where actually you're coordinating multiple applications at once with individual models. And again, you have to have some kind of routing between them. It gets a lot more complicated, and it looks a little bit more like, enterprise style, workflow systems, but, with high performance and much larger scaling. So LLM training is a specific type of AI workflow, I'd argue, and looks a lot more like these other cases I'm showing here. And as we all know, failures in these systems are really, really costly. So we can look at, how do we make, let's start with something simple. There's data loading and things like that, which are, challenges unto themselves. But for today, I just want to focus on the checkpointing and restart aspect of things. So, young daily optimization is important here. So really what that comes down to is how do you make checkpoints really fast? How do you make it easy to recover? And how do you actually do that when you're looking at an ensemble of applications running together rather than just a single like MPI style application? So efficient, portable solutions, I really want to stress that portable aspect of it for checkpointing and persisting workflows is critical. And the reason I wanted to stress that portable solutions is the space that I'm coming from is really the Python developer community. And it's really not of great interest to have to write a lot of code specific to different system architectures. So they want abstractions. And so that was really what we're after in this work. So the project I developed is called DrAgOnS HPC. It's an open source tool that we've been working in collaboration with people with folks at Argonne and some other institutions as well. And it's really distributed Python runtime. It provides the multi-processing API for those who are used to Python. But relevant for today, we're really going to focus on this data API, which primarily consists of an in-memory distributed dictionary. And what we're thinking, to kind of give you a little of where we're headed, it's that coupling of that in-memory distributed dictionary with DAOS is something that we wanted to investigate. So we're kind of early in our DAOS journey of being a middle layer that can lift DAOS up into the, into user applications, maybe in a sneaky way without them even knowing. But along the lines, we have this AI API that's really around orchestration of PyTorch processes and also some data loading features, and telemetry and our workflow APIs are all relevant too, but given time, I'm going to just focus on the data API. A couple of key things though, this, despite it being a distributed Python tool, we've scaled this over 3,000 nodes on Aurora, and we'll plan to keep on scaling up. We support Slingshot, InfiniBand, Ethernet, all the different types of GPUs that HPE really mainly deals with, and lots of different execution environments. So focusing it on our in-memory distributed dictionary, a lot of this, has similarities to, some of the DAOS features. But what we're doing differently here is this is an entirely in-memory solution built out of the communication infrastructure that we have in our runtime. Our runtime has to facilitate dynamic Python functions running in independent interpreters, communicating with one another, and then exchanging data. So we needed a solution for that style of communication where processes come and go really, really frequently, and also be able to share state between them. So something like a dictionary is a very Pythonic sort of expression of how to store data. So we built out of our communication and memory management layers that we had to make in order to do a multi-node implementation of Python multiprocessing. We built a distributed in-memory dictionary out of that as well. So some similarities there. We have the concepts of these managers, each of which are responsible for shards of the data. They can live wherever on the system. They could be, all on one node. They could be distributed across all of the nodes. And client processes can transparently access the memory from anywhere, as long as it's within the runtime. So you can do things like, create a small little dictionary for one use case and right next to it make a really big one. We were doing things like that with our colleagues at Argonne, building out some drug discovery workflows that we're scaling up, and that's the case that we're running at around 3,000 nodes right now. Where DAOS comes into this is we wanted to build out the capability of taking our dictionary and actually persisting it, because it's ephemeral. It lives in memory. We can use it for things like checkpointing in memory, but if catastrophe hits, we need a place to put that information. So we built out an abstraction layer within our dictionary that lets us use different backends. So we have a POSIX backend and a DAOS backend now. And what we decided to do here is actually use PyDAOS to implement this. That was really something that we wanted to explore and understand, what are the limitations of PyDAOS, where should it head to help facilitate these types of integrations into other tools. So we have a working prototype now. It's actually out in our current release. So if you are interested in taking a look at this and trying it out, it's just a pip install DrAgOnS. Everything you need is there. What's interesting about our implementation is user processes, user applications have no dependencies on DAOS whatsoever. That's all managed by our dictionary managers. That's actually where the DAOS client API gets used. So done the way we have, users will just tell our distributed dictionary, oh, we want to use the DAOS persister backend. And under the covers, we'll attach to that particular pool in this example, create containers and dictionaries within there for them, but the user application doesn't really need to know anything about that. What they're doing is interacting with what looks like a regular Python dictionary that has some added features for the concepts of checkpoints, and so I got a little piece of code there. And then what happens is, on some frequency that users can define, they can persist that data out to DAOS. They can checkpoint at really high frequency because that's probably in memory, and they can at a slower frequency just to persist that out to disk to handle catastrophic failures. So just as a simple example, we have a small internal system that I forget the exact configuration of DAOS. It probably doesn't matter too much in this example, but what we're doing is we built just a little benchmark to emulate what happens in FSDP training, so this fully sharded data parallel. So each client's got kind of some unique state, but there is replication of state, and that's important because it allows us to, implicitly from the algorithm, we've got recoverability because we've got multiple copies of different client state. So we'll do 8 clients per node and just checkpoint, what would presumably be a large tensor from training. And in this benchmark, we're just checkpointing constantly and persisting constantly, just to see what the overheads could be. But the important feature is this persistence is asynchronous. So again, the idea is that clients can checkpoint in memory quick and asynchronously spill out to DAOS at some other lower frequency, if based on the performance characteristics of the DAOS system. So this was just a proof of concept to show, yes, it holds together. Our in-memory checkpointing is faster than DAOS, it's faster than POSIX, but gosh, it darn well better be, otherwise it's not useful. And then of course, not surprisingly, DAOS is crushing NFS on this little test system. But it was just proving out that whole end-to-end workflow of checkpointing in memory, writing out to DAOS is working. So we're now working with our HPE DAOS team, so special thanks to Mohammed, because I know he's been working closely with our team on this, and with the Argonne folks. I was unable to get DAOS data for today. We're going to get it very soon. There was some work being done on DAOS when we were, time to gather the data. So this is where we got to now. So all I can say is from the test system, we know that the solution's functional, and we're working on actually gathering end-to-end performance data. But a couple of key characteristics. We just scaled this out to 512 nodes on Aurora. We can go larger, as I've said before. But important things, the in-memory checkpointing should be completely scale-free. Indeed it is. And even though it is scale-free, of course the data can be accessed from any other node if you want to grab another client's state. The checkpointing is quite a bit faster than to the Flare Lustre file system on Aurora. So that's telling us something like in this solution where you've broken out checkpointing and persistence into two different things, and doing those at different intervals, you can persist something like every 5th checkpoint. So that means if something bad happens, we can first try to recover from in-memory, and if that can't happen, then we try to recover from the persisted answers inside of DAOS. We've actually taken this prototype and applied it to a Llama 3 kind of training scenario using FSTP, and done things like gone in and randomly shoot processes and proven that DrAgOnS able to recover the training, recover it from the in-memory dictionary, and then also reload it in the case that state isn't sufficient from memory, reload it from a persisted file system. So just a couple other things. Our dictionaries, it's outperforming Lustre in this case, as it should, and we'll be gathering the end-to-end performance data on DAOS hopefully in the coming days. And I actually have a link where we're going to be providing more information, including sample code, so that you can kind of take a look at how this gets written from the user's perspective. It's all normal Python-looking code, shouldn't look too surprising. And again, they actually don't see DAOS. They just tell our dictionary use DAOS. And so in terms of an adoption, that's about as easy as we can make it, right? We've removed the need for any code change other than saying use the DAOS persister. So a couple of conclusions. So I just gave you a super fast overview of what Dragon HPC does. So again, it's this open source tool that we've been building out for these Python and Converge HPC AI use cases. This high performance in-memory checkpointing and persistent solution is really important for all the different types of use cases we have. And this integration with PyDAOS, went relatively well. I think that, I've a couple of comments on PyDAOS is like, we definitely need to keep that going forward, improve it, and I think it's going to be a really important tool to facilitate integrations into other tools as well. And I think I've heard some similar comments from others today, so I completely agree. I think also that idea of splitting out the client from the rest of the code, I'd like to be able to pip install the PyDAOS, that would be great. The other thing I'll mention too is with the design we've got, we were able to leverage batch puts really, really easily. And again, the user didn't even have to know we did that, and that really drove up performance a lot. So those are really some important things. But yes, here's some QR codes if you want to learn some more and take a look at some sample code. And again, the performance data will be updated once we've got it in a few days. So that was kind of a quick, but I know we're short on time, so I wanted to go. Any questions? Yes.
So for PyDAOS, we're using the container interface or the PyDAOS summary?
The container interface, yeah.
Any other questions for Pete?
In terms of PyDAOS, did you try libDFS or I don't know, do you have any thoughts on the file system at the lower level versus just the straight?
We were just using straight PyDAOS. Like I said, we're kind of early in this journey, and we're kind of getting towards basic good scaling and performance, and then batch put is kind of the layer of complexity we're at right now, making sure we're using that well. But I'm sure we'll run into some of these other fine-tuning things as we scale up. Yeah.
All right.
Thank you.